So let's go ahead and get things started today. I'm Steve Perczewski. I'm on the product management team, product marketing team here at Vast. I'm joined by Kyle, and we're going to talk about the impact of AI on HPC, specifically focusing on energy research. This is important, obviously, to HPC shops, but it's got a wider implication, especially with the spread of AI. So it's important not only to HPC, but also to, say, enterprise customers that are thinking about AI. So I'm joined by Kyle. He's our CTO focused on HPC. He's got extensive experience. Kyle, please introduce yourself.
Hey, Steve. Hello, all. Kyle Lamb. I've been with Vast for a little over 3 years, 3.5 years, I guess. Prior to that, I was at DDN, and prior to that, I was the storage lead at Los Alamos National Labs. So I've got about 14 years of HPC experience. I joked at the Rice conference about being a angsty teenager in my HPC experience, and also in the fact that once I get to 21 years, I will be able to drink in the data center, which I think that's the goal. That's the target, right? The 21st year of I'm going to work at least 7 more years just so that I can have a drink in the data center.
So that the sign on the outside of the data center where it says, no food or beverages doesn't apply to you anymore once you hit 21. That's pretty awesome.
Once you have 21 years in HPC, that is the rule. So yes.
That's phenomenal. So you bring up a good point today. We're going to dig into, you gave the session at Rice. There's also a session by TAC at Rice. We're going to kind of use that to guide our conversation. And this kind of brings us to what our agenda is, right? So we are going to build around what you talked about there, talk about some of your customers, and talk about, how things are changing rapidly. This is a pretty small session, right? It's focused really heavily on HPC, and we're saying energy specifically, right? So feel free to click that Q&A button. We'll take your questions. These sessions are always so much more fun and really valuable when we get a conversation going. So click on that, and I will relay your question to Kyle. And again, we can dig in really to anything you want to talk about. But we do have a specific one, so I'm going to go ahead and move on here. And I wanted to, Kyle, kind of get some of your impressions. You were obviously, you presented here. You are, TAC is your customer. And there was a session by Dan Stanzione. He's the executive director at TAC. And he really got into some of the futures and the way that AI is impacting HPC. And for me, what was surprising was when I first started watching the session, I didn't attend in person. I thought he was talking about AI models, AI being used in energy research. And more what he was talking about was like all the money is essentially going after AI, and all the vendors in the HPC space are now chasing that money. And so that's having a profound impact on the infrastructure that will be available to HPC shops and practitioners. Can you dive into that a little bit for me?
Yeah, I think HPC has kind of been in this situation a few times, right? Where there will be a buzzword type of thing or a buzz type of technology that comes along, and that actually generates a lot of funding, right? And it becomes something that's relatable to the funding sources for HPC, right? And so in my own time period, like I've gone through a couple of them, one of them being like whenever big data became a really huge selling thing, right? And everybody was attaching big data to, every one of their proposals or their requests, right? Or talking about how they integrate with it, big data. I would say that AI is much, much larger than anything I've seen in the past, right? Because it's affecting not just the software models, but also a lot of the hardware models that are being utilized, right? So it's kind of a multifaceted effect to the system, which actually, as like Dan, I believe, said in his presentation, it kind of harks back to the times whenever we went from having large scale mainframe computing to actually having, clusters, right? And adopting, the use of x86 or other processors and building out clusters to be able to accomplish HPC workflows. I think that we have sort of that same generational change where a lot of the code sets that are being utilized for HPC will adapt and adopt some of the AI things, but more impactful will be the HPC adoption of AI hardware, right? And things that are generated for AI.
Yeah, I think that makes a lot of sense. It's interesting. He was talking about some of the way equipment's being reused, the changes in networking. So it's not, my initial thought, oh, it's GPUs for everything, right? But he's talking about new networking technologies. So really profound impact. I thought that was super interesting. So one of the other kind of questions that I had for you is like, you know, how do the practices changing, right? Because I kind of think about, HPC classically as being these very large systems that are used by a smaller number of customers, and now it seems like they're getting a much larger number of users, and it's much more applicable.
Yeah,
And
I
how
think
does
that there
this?
are. Okay.
I was going to say, it's so like reliability becomes a lot more important, like the basics of HPC practices.
Yes, I think it kind of you can harken that back to the original use cases for HPC, right? You had a lot of modeling and simulation, and a lot of that modeling and simulation was very focused on a few user sets, right? You had a few codes that you were running to do a very important job. And as HPC has adopted more and more use cases and had more and more customers, to include AI ML, right? Because most of the HPC centers are actually running a lot of AI ML jobs at the same time, kind of co-resident with HPC jobs, classical modeling and simulation. And it has made the amount of workflows that are running on the HPC clusters larger. There are still a subset of, exascale style systems that are really generated towards large, single or single job take up, most of the compute resource that are
Mhm.
actually doing HPC end up with a huge amount of mixed IO and mixed workflows that are actually happening concurrently on the system. And that has some pretty significant impacts for storage within the system.
Makes sense. So I've got a few kind of choice quotes that Dan gave that I thought were kind of interesting, kind of spark some conversation here. So the first one is around Lustre, and I know it's a huge deal for TAC to move away to Lustre and adopt VAST. I think his actual quote was, "Any one user can kill Lustre if they're pathological," or something like that. And then I think he went to creative. Explain to me why
Yep.
this is such a big deal.
It's a big deal just because the design and development for Lustre and a lot of the parallel file systems was designed around, that 20 or 30 years ago time frame. And the thought process was we really need an efficient way to do checkpoint restart. That is the whole goal for these parallel file systems, right? And that's an important thing for HPC, right? Checkpoint restart is an important thing for HPC, but as we bring in more and more use cases and more, customers to these same systems, the ability to do checkpoint restart becomes more difficult because you have a lot more mixed workflows, right? And these systems were kind of designed around having one large sequential job that was writing to the system. So you take, a AI job and an HPC checkpoint restart, and you happen to have them doing IO at the same time, and you're going to get very, very mixed results out of the system, right? And so, VAST as a solution actually can address that a lot better, right? Mostly, there's a lot of that is actually related to just the hardware, right? We're an all-flash storage system, so we can access all of the data, irregardless of, seek times on hard drives and things of that nature. But there's also just some really great benefits within the way that we architected the system, right? And so it makes it a lot easier for us to address that and to remain stable even whenever we have this very diverse workflow, right? And in the case of a pathological user with Lustre, you can kill it. I won't say it's easy, but there have been plenty of times that people have done so just because they didn't realize what they were doing, right? Even in the IO 500, there's a test case in IO 500 that I believe came from a user at LANL. And the workflow itself is to do these IOs that are just smaller than 4K, right? And doing that to a 4K aligned system just drives it nuts, right? Because you're constantly doing multiple seeks just to do all of these data writes and reads. And so things like that are things that can easily cause issues for a classical parallel file system that's really developed around, a hard drive and an aligned IO size, right? In our case, we don't have an aligned IO size. You send us something that's not 4K and we don't care. And so it is a neat thing, and it is excellent and amazing to see Dan kind of saying that, that he was seeing benefits from this as well, and that in general that they really were trying to hurt VAST and bring VAST down. And they were unable to, besides maybe a hardware failure that we had. And so a really nice statement that he made there. And it's a really cool thing also, if you look back on Rice conference the year before, there were a lot of comments about how they were going to start testing VAST and, how they had gone through kind of a POC phase. Tommy Vineyard was saying they've gone through their POC phase and that they were happy with what they were seeing. And to this year's conference just was a testament to the fact that we're delivering on that, right? And that they're still happy with what we're able to do.
Yeah, I think that's a fantastic point. I know I liked in Tommy Minyard's discussion, he talked about that hardware failure, and it actually wound up being kind of a positive because he's like, he had a hardware failure and it didn't matter, right? It's like the system kept going. And that, for me, coming from the enterprise side, I don't have deep experience in HPC. That's surprising, right? That you would, but of course I can have a piece of hardware fail, but it kind of shows kind of the convergence of all worlds. The other thing that I think was interesting you brought up is it's not necessarily, he also made a point about like Lustre is written for perfect code. And I think in our discussion the other day, you mentioned that, well, it doesn't matter if your code's perfect if somebody else's code isn't, or it lines up the wrong way. So as cloud service providers are now starting to offer, and there are service providers doing HPC services, it would be very difficult for them to build something on top of Lustre if they're going to open it up to the public, right? That's like, how do you don't know what you're going to get because you're going after everything.
Exactly. And it only takes one pathological user out of the whole set to cause issues for everybody, right? I spent a lot of time trying to track down who was using all the metadata within a system, right? Who's hogging resources and doing some silly things like, generating millions of files in a single directory or things of that nature, right? And trying to find out who that was and track them down and, educate them on how to actually utilize the file system in a better way. It was a difficult thing as a storage admin to do, right? And the nice thing on the VAST side is that we handle that, and we can, basically we will we have multiple ways of dealing with it. The system itself is going to push back on some pathological use cases anyways, and so it's going to slow those down a little bit. And B, we can actually use quality of service to implement an additional layer of protection on top of that. And that's what a lot of the cloud service providers are using with us now, is they're actually saying, here, I'm going to allocate these resources. It's going to be, X amount of capacity and Y amount of performance, right? Both in IOPS and in bandwidth. And if I set those, then this one, customer in this case, or one user in a HPC center isn't going to be able to clobber the system and cause, ill harm to other jobs that are running, right? And you can change that dynamically on the fly, which is a pretty amazing thing.
That is awesome. So we'll move on to the next quote. And again, I like this one because I'm in marketing, right? But we're actually getting compression out of our scratch data. So like, tell me, why does this matter? Why, the fact that we can help people do data reduction, even in high performance environments, what's the benefit here for the customer?
The biggest thing is that we're able to give them more flash for their dollar, right? At the end of the day, if everybody could have all flash all the time, and if they could have everything fit in memory and they had reliable memory, that would be what they would do, right? It would be all high bandwidth memory, and it would all be stable, and everybody would be happy, and you and I would be out of a job. But that doesn't exist, right? So you do have to do checkpoints, you do have to do these types of things, and memory is very expensive. The next scale down is flash. Flash is more expensive still than hard drives. But if I can give somebody 2-to-1 data reduction, then I am reducing the price of that flash in half, right? And so the fact that they're able to see compression on their scratch data means that they're getting, more capacity per dollar than what you would typically expect to see. And that varies depending on the data sets, right? But the fact that scratch data is getting that grade of compression is pretty it's very nice, and it's to a lot of the HPC centers, it's pretty surprising, right? A lot of sites used to use Lustre with ZFS, and ZFS has an LZ4 compression that it utilizes. And you would see like 30 to 50% compression ratio on that, right? Mostly I saw around 30% at Los Alamos, right? So 1.3 to 1. The fact that we have large scale HPC centers that are seeing, 1.8 to 1, 1.7 to 1, even all the way up to 2.5 to 1. That is a pretty significant data reduction, and it is a huge value for them whenever it comes to, cost per byte of flash. I actually have some sites that are getting some really insane compression ratios, right, or data reduction ratios, like 4.5 to 1, right? Admittedly, that's more project space where there's a lot more usage of the same kind of data sets or the same code sets that are being utilized across the board, and we can get excellent data reduction on that. But any kind of gain that we're able to offer to our customers just reduces that cost per byte of flash, and that's a huge win for them.
Nice. Makes a lot of sense. Does it also do anything like, so I know within AI, talking about pipelines, what we're saying is you don't need to make additional copies of your data. Is there the same benefit in HPC where I can just leave data in place and operate on it in different ways?
Yes, you can have the same data sets, and if you actually do make multiple copies of the data, it doesn't matter too much, right?
That's right. It just gets deduped
So
anyway.
it just increases your data reduction ratio that you're seeing in the system, right? So people who are doing that, like there are a lot of use cases where people are making multiple copies of data because the users don't have the right thought process about how to utilize it, right? And so they have multiple people wanting to access the same data set, and they make multiple copies of it. And with the VAST solution, it's still going to look like one copy to us, right? And so yes, those always are. It's kind of a strange thing, but like it increases our data reduction ratio pretty significantly. And so we are completely fine with having multiple copies of the same data on the system, right? So although with the VAST system, you don't necessarily have to do that, right? You can actually process on it. We have parallel locking on the system, so there's no need for you to have multiple copies to do, different updates to individual files or things of that nature.
That makes sense.
Yep.
So let's dive into some of your customers. I wanted to talk about NREL. So you've got a lot of experience here. Can you kind of tell me, how did we get started at NREL?
So actually, I had a customer relationship with the storage team at NREL pre joining VAST, and so whenever I joined VAST, I talked to them a little bit as well. And so I've known NREL ever since I was at Los Alamos. Whenever I was at Los Alamos, I went up and visited with them, and we would talk to them. We had a lot of these large-scale meetings where you would bring in, multiple different national labs to talk about, different aspects of what they were working on, right? So I would do a lot of presentations about storage things that I was doing, right? I would talk about campaign storage whenever I was leading the campaign storage effort, and that would be presented to all of the national labs. NREL was always the one that came in to talk about energy efficiency, right? And for a while, I actually was working as a one of the managers for the infrastructure team or the facilities team at Los Alamos. And so I actually had to put on a completely different hat and talk about facilities a little bit. And facilities are for HPC centers, it's an amazing topic that is very in depth, and it is by no means a simple subject to talk about. And having really high energy efficiency in a data center is something that is not all that common, right? So on this page, the smallest text on this page actually says annualized PUE rating of 1.036. That PUE rating is astounding. I mean, astounding. There's not many sites that can get to that level of PUE. And I think it's the best in DOE, and is very competitive across the board against most data centers. Most data centers are much, much higher, right? If you can get, I know like a lot of times you're targeting to get to like a 1.5 to 1 D or PUE, right? So anyways, they're very energy focused, not just for energy efficiency for their data centers, but also in the work that they do. They do a lot of renewable energy work. So a lot of their customers are, wind turbines, geothermal. They have a lot of oil and gas that come in as well. For a long time in their data center, they had a gas engine that was sitting in the middle of the data center, encompassed in this little bubble, right? that they were doing testing on, and they were doing monitoring right next to an HPC resource so that they could actually get more information from it. And so anyways, it's a really interesting lab to go and visit. If you have the chance to go and see their data center, I highly suggest that you do. Don't bring a jacket because you'll walk in and it's a nice toasty data center. I was breaking a sweat whenever I was working in there and putting in some hardware a while back, and so it's a very different data center that is very intriguing in that sense. They do have a couple of really large scale systems. Right now, they're kind of transitioning, right? They typically will have one very large scale system that's in production. Right now, they have two because they're retiring Eagle and bringing in Kestrel right now. And so this is an exciting time for them. You can see both of those systems in these pictures here, right? The Kestrel system is in the middle there, and Eagle is down on the lower right. And there are significant systems, especially whenever you're talking about renewable energy and energy research, right? And so it's a pretty interesting workflow that they have as well. And so whenever I started talking to the storage admin, Mike Solari, about 5 years ago, or actually, I guess it was about 4 years ago. Anyways, he was talking about some of the pain points that they were having. And so that kind of generated a lot of talk about what VAST could offer and what VAST was doing for them. And so this is a lot of the things that we discussed at that time, right? They had a lot of data silos, right, amongst multiple clusters. Each one had its own storage system, and users would have to copy data between storage systems in order to have access to data. They had upcoming AI ML workflows. They actually had a few GPUs on Eagle, but they knew that they were going to be increasing the number of GPUs and increasing the performance of the GPUs whenever they went out to Kestrel. They had one of their main issues was actually the small mixed IO performance in the system, right? So they are definitely fitting that category of being an HPC resource that has many customers running concurrently on the system, right? And it'll vary depending on how much resources each one of those customers are taking up. But I don't think they ever run many jobs that are just one user taking over the whole system and having direct performance on the IO subsystem, right? So everything ends up looking random for their IOs, right? No matter what's going on, they always have, multiple users accessing the file system at the same time. And so they had a lot of issues with, small IO whenever they would have heavy writes going on to the system, right? Because if you're doing a checkpoint restart, that tends to, especially with parallel file systems, that tends to dominate all of the workflow for the storage IO requirements, right? So your small IOs will get swamped by these really large, sequential writes from a checkpoint restart job. And so they had some issues with that for some of their customers. And these are important customers that they wanted to be able to address. And so they were looking for a way to have, better small IO and mixed IO performance. And then the last one was a data provenance thing. This actually came up a little bit later. It wasn't one of the things that was at the very beginning, but it's a common problem amongst all of the HPC sites, right? And across, science in general, right? You really need to know where your data is coming from. And this is actually, it's kind of an interesting thing, right? We're in this dynamic time now where I'm listening to the news that my family is listening to, and AI is being brought up all the time, right? So AI has become so much more of a pop culture type of discussion or a in the news type of discussion. And data provenance is actually driving some of the concerns with AI ML, right? If you don't know what data you're bringing into the system, how do you know what you're going to get for your results, right? Because there's going to be a lot of bias based off of data that you don't know where it came from. And so I think data provenance itself is just becoming an escalating requirement for most of these sites as well, and something that we are working with NREL to help have better tool sets to utilize.
Yeah, I mean, from the scientific, this is science, right? So everything has to be repeatable. So you need to know exactly where the data came from, what data set was used for any given test. And that, like you're saying, it's big in AI, but I imagine it's just as important in HPC. So there's a lot of crossover here, and I know we're using our data, and now you're going to cover that a little bit later, but it's definitely a really interesting area that I hadn't thought about before.
Yes, I was at a conference 2 weeks ago, and there was a long discussion just about being able to recreate a job, right? And so even with code sets. They actually did a job where the scientist was actually targeting to make their code completely reproducible, right? So they packaged everything up, right? They said, I'm using these libraries, I'm using this, tool set, I'm running on this system with this many nodes, this much memory, all of those things. They bundled it all together and said, this is what I was using, right? And they went about a year later and tried to reproduce it, and they couldn't,
Hmm.
even though they were making every effort to try and make it reproducible. And so, yes, data provenance is going to be a very important thing. And the more input we can put into the data provenance, the better we're going to be, or the better off we're going to be, right? It's not something that we can all, or that has a simple solution for it. But the more tools that we offer, the better off everybody can enable it.
That makes sense. I think I wanted to ask the next question about like the data silo topic. Explain this to me. How important are composable systems?
For HPC centers, they're pretty important, right? Being able to have a system that offers the same data to be available to multiple different sites, right? Multiple different clusters, and multiple different users, right? And use cases. It covers every single HPC site that I've been to, right? There's not very many places that have just a single site and a single cluster with a single storage solution attached to it. There are some that do that, but they also then will have another system that actually is external and that is a lot more available, right? And it just simplifies things because users don't want to move data around, right? It just adds time to their workflow to have to move data to another system. And so having something that is composable allows them to have the same data at multiple different HPC clusters, right? Which means that the users can run wherever they need to, right? If there's cycles available on computer or on HPC cluster A, they can go there, or if it's on B, they can go there, right? And the way that VAST is doing it is much more interesting as well, because each of those pools can be its own quality of service domain as well, right? And so in a lot of cases, like say NASA Ames, we have a set number of compute nodes, right? C nodes, that are actually exporting the namespace into 3 different clusters. This is important for a couple of reasons. One, they set how many of those nodes they want to each one of those clusters. And two, it actually doesn't make a cross-domain broadcast domain, right?
Okay.
If you have to have something like routing between all of these different clusters, what you're enabling is a fault domain that can actually cross across all of them as well,
Makes
right?
sense.
And so by us not having a shared broadcast domain amongst all of those clusters, we don't introduce any issues where if something happens to one of the on cluster A that there's a broadcast storm, it doesn't actually end up going into cluster B or cluster C, right? Which is a pretty significant gain for those clusters as well, right? Because oftentimes, cluster B is a alternative to cluster A if something goes wrong, right? And if you have a case where cluster A has issues, doesn't happen very often, but whenever it does, it can be catastrophic to the entire system, right?
Makes sense.
Yeah.
Yes, the reliability goes up substantially with that. So that makes a ton of sense.
Yes. Yep.
So I wanted to talk about some other workloads here. So you gave an example in your talk about AlphaFold. And I thought this was interesting, right? Because it kind of like digs a little more into, kind of how VAST works versus a parallel file system in quotes. Explain a little bit of this, and I have just a few questions. So jump in.
Yes, no, this is actually a really nice example of us doing more things with AI ML, right? I think that for the most part, VAST kind of started out as an enterprise storage system and did a lot in HPC because HPC was willing to adopt us early, right? Because HPC is always a little bit more forward looking with what they're looking at for technology, and so they adopted us early. But as we started to move into AI, we did a lot of testing with different AI structures, right? AlphaFold being one of them. And this is actually research that was not from VAST, right? This was actually another user who was actually just running on multiple different systems that he had access to. And he was running AlphaFold against each of them and looking at the storage differences that he was able to see and looking at the overall runtime that he was able to achieve based off of each one of these, right? And so as you can see here, right, all of the vast run times were much lower, even when comparing to an existing storage system that was also all flash in some of these cases, right? And so the fact that we're able to get a lower runtime means that you're able to get a lot more science done, right? And you're actually able to keep your GPUs and your resources a lot more active, right? Because anytime you're waiting on I/O, um, the processors are twiddling their thumbs, right? If you're looking at how fast processors run, it takes an eternity to get data to them in comparison to how fast they can actually operate. And so the faster we can get the data to them, the more they're going to be able to make progress and the more science that we're going to be able to accomplish. And so this is an actual use case kind of just demonstrating that. And a lot of this is actually related to the architecture of the system as well. So going into the way that VAST actually does its architecture, there were some fundamental trade-offs that we decided to advance, right? We decided not to use hard drives and not to enable hard drives in any way, shape, or form, because we wanted to actually facilitate this type of a workflow, right? Something that was much faster, that was actually born in the all flash timeframe, right? And that didn't do anything to try and address a hard drive solution. And there's some major gains that can be accomplished with that, along with the way that we do our metadata, right? And so both of those are what actually ends up allowing us to get much better performance on this this workflow. Along with that, you know, there's on the metadata side of that, right? The fact that we are doing our locks down at the actual metadata level on the system means that as soon as we lock a region of data, it is known to everybody, right? There's no communication that has to occur amongst different nodes to say I have a lock state that changed. And that's a huge gain for the system, right? Because it's an instantaneously recognizable lock state within the system. And if anybody goes to try and access it, they see the lock and they don't have to communicate with any other node to find out whether or not there is one. And so that's a very fundamental change within the system that actually enables us to have a lot better performance on things like this, especially when using something like mmap, which AlphaFold uses pretty extensively.
So we've got Lustre with DDN. CephFS that's Ceph's parallel file system, correct? So, and what are we using here? We're using NFS over RDMA in this case, or?
In this case, it is NFS over RDMA. And so pretty NFS over RDMA has been around for quite a while, right?
Yeah.
It had some bugs in it originally. And so whenever VAST first started up, we built our own driver to address those bugs. Our driver has been in diminishing requirements over time, right? As those features that we bring out with our driver are getting adopted into upstream. And so most of the features that we have within our driver have actually been adopted upstream. There's a few corner cases that haven't been adopted yet. Like we're looking at doing a job ID within the VAST driver. And if we're going to do job ID, that's a pretty critical, or that's a pretty nice feature to have for HPC, right? It may be a pretty nice feature to have for AI/ML because AI/ML ends up kind of riding the coattails of HPC in a lot of ways as well, right? They're using a lot of the same schedulers, they're using a lot of the same features. So that may or may not get adopted into a standard NFS kernel, right? But for the most part, most of the things that we are actually developed with our driver are kind of being adopted into the standard kernel and making less and less importance for us to have our driver. But NFS over RDMA has been around for a very long time, and it actually offers really excellent performance for systems like this, and is very nice for HPC.
Makes sense.
Yep.
Let's talk about some small mixed IO performance. This is something that was important to NREL. Can you explain a little bit?
So they have this really large data set that is like I suppose it might be older than me. Anyways, It's a data set of wind data, right? And that wind data is something that they are constantly, scanning over, right? And looking back, right? And it's a few things, right? One, it is a pretty important data set, right? To have, that long term of a set of data about wind, right? It's something that you want to make sure that you have,
So
protected and known, right?
people are using this to decide where to put like wind farms.
Somewhat, I think there's multiple
Okay.
use cases, right?
Okay.
So I think there's use cases for where to put wind farms, right? That would be one, but there's also use cases for what's happening within our atmosphere and what's
Uh,
happening within,
Climate modeling. Yeah.
changing wind within the system, right? So there's a scientific just discovery side of it, and then there's also an application side of it for things like renewable energy. But the big thing is it's a large data set that they were accessing in a very small random way, right? And oftentimes whenever they were doing that with the standard storage on the clusters, they would run into interference with other jobs that were running, and they may have some performance bottlenecks. So they had some variability in their job runs, and they also had some slowdowns, right? With the addition of what NREL calls campaign storage, their vast cluster, they were able to see like a 5 to 6 x improvement just by having it be an SSD based system. And this is actually without having a lot of resources allocated to it, right? This was connecting up to Eagle with just a few of our C nodes. And even with a few of our C nodes, just that low latency access to small IOs increased their performance on this one use case significantly. That's something that we've seen across the board at a lot of the national labs, right? We'll have a lot of um, users who will come up to us and say, yeah, I was working at this national lab and I was having troubles making this work with, the standard parallel file system. And so I went to the admins and they said, go use VAST.
Hmm.
And I went and ran my job on VAST, and all of a sudden it worked beautifully and I was able to get the results that I wanted, right? And so VAST really does address, a lot of the workflows that typically are pain points for parallel file systems. Well,
Yeah, one of the
also, you scale it up enough to actually address the parallel file system workload, we can actually address that as well, right? So it can be the best of both worlds. You just have to make sure that we, build it to address a parallel file system workflow.
makes sense. Yeah, one of the first HPC customers I talked to said that when they got VAST, they just put the problem child workloads on VAST, things that didn't work anywhere else. They put on VAST, and yeah, kind of like to your point, that's how we got started. So I thought that was kind of fascinating. So I want to dig into the VAST catalog, going back to that provenance and what else do people
Yeah.
use this for? So it's a really interesting feature.
Yes. So I think this is a storage admin's dream in a lot of ways, or somebody who wants to know what all is going on within the system stream. So the catalog allows us to have results, basically a database of all of the metadata stored within the system. Whenever VAST brought out our tabular format within the system, we wanted to, utilize it, and we wanted to have some really great examples of how to utilize it. And taking our own metadata and throwing it into a tabular format and making it accessible within the system was one of the nice ways of showcasing this new tabular format. And so the catalog actually came out before we actually had the database release, or the tabular format database released out to all of the customers. Um, so the catalog itself is a dream for admins because it allows me to answer questions, right? I oftentimes would get questions about who's using all the storage in the system, right? How long are they keeping their data around? On average, how long are people keeping data around? When was the last access time for, this giant file that is in the system, right? All of those types of things I can easily just run a query and give answers for, right? And so if the boss is asking me, hey, why is who's hogging all the resources on the system? And they have, users can be sneaky, right?
Mhm.
They might store some of their data in, you know, a group shared directory, or they might store some of it in, you know, their home directories or other locations, right? And so sometimes it's difficult to find out exactly who's using everything. You can do some of that with quotas, typically, if you have user quotas enabled across the system, but it's so much easier just to run a query and say, tell me how much data, you know, Kyle is using within the system. And that way I can go and yell at him and tell him he needs to delete data. And it's even more powerful whenever I can say, Kyle, you have data in here, right? That, you know, 90% of it hasn't been accessed in 3 months. Why are you keeping it here, right?
Yep.
And so what is the importance of this data that you need to keep it around? So it just allows you to answer questions, and it's very powerful in that sense. More than that, it actually gives us a way to interface with you know, something that might be able to migrate data to archive or migrate data to another location, right? It just gives us
Right.
a powerful tool set to know more about our data and know more of what we can do. And as AI/ML comes along, I think AI/ML might be able to do more with this as well, right? We can all of a sudden start to have more information about our data and about what's happening within it, because AI/ML models are very good at sorting through some of these things and looking for changes and,
Oh,
you know, analyzing what's happened, letting us know, which is
so you can kind
another
of
key
do
feature that we're
a
ingesting
diff.
into our database, right? So if we have all of the
Yeah.
access, exactly. All of a sudden, we have all kinds of information about what's happening within the namespace. And that's a very powerful utility. And if we have AI/ML start to look at that, it becomes incredibly powerful, right? On here, this is different than what's happened in the past, right? As I've studied these data access patterns, this looks very different. We need to do something here, right? And having a very large scale audit log as well as a nice catalog of all
Totally.
of the metadata allows us to do that.
That's true. So the
And
audit is in
having
here as well. And you can expose this to like
audit,
Spark and Trino and use like advanced query engines. Very, very open.
exactly. Yes.
Well, let's keep moving here because we're starting to get a little short on time. And again, everybody jump in, ask questions. If something Kyle said was interesting, hit that Q&A button. We can talk about it. So tell me a little bit more about NREL's environment and about how they're using
Uh,
this.
s- yeah, so they had an initial deployment that they used for campaign storage. It was what we would consider a 4x4 system, 4C boxes and 4D boxes. It was about a 8 petabyte system, right? Because they were seeing about a 1.8 to 1 data reduction ratio on the system. They since expanded it by another 2C boxes and 2D boxes. And so now we're at about an 11.8 petabyte system with that same data reduction. All expansions were done online. You know, everything was added to the system while things were working, and so it's a pretty nice way of being able to do those expansions, right? Doing online expansions is something that's a little bit different for you know, a classical parallel file system. um, and then the other side of that, you know, they've got about 10 petabytes stored in the system as of now, and they are seeing that 1.8 to 1, which means they, you know, actually bought, you know, a little over 6 petabytes of storage, but they're seeing 10 petabytes of data
Usable
stored.
space.
Uh,
That's awesome.
and then the uptime, yeah, the uptime on the system is at 5 nines, which is pretty amazing. And it would be 100%, right? From the time that we deployed it, but I made a mistake. Early on, whenever we were standing up the system, I just put in kind of a spoof IP address for a DNS round robin. And the first time we did an upgrade, it was actually taking those down one by one. And they weren't able to reach that DNS server. And so they started to fail over, right? And it caused a little bit of an outage because they were failing each other over. We quickly figured out what it was, fixed it, and engineering has now fixed that so that, you know, if some other idiot like me puts in a spoof address for the DNS server, it's not going to cause them to actually go down. But other than that, it's been 100% uptime, including upgrades. I think they've upgraded about 6 times for versions and OS. And then they've also done that expansion. So, and a few hardware replacements. I think we've replaced a couple of C boxes and a couple of D nodes. So it's been a very reliable system,
Nice.
which is really nice for me as a person kind of supporting the customer, right?
Right.
To not have to deal with a lot of negative outages and things of that nature.
Yeah. I've
The
been in that
usage for the
situation.
system. Yep, they've got connectivity to Eagle. They've got some campus networking. They also have connectivity to Globus so that they can do external shares. We're playing around with S3 with them, as well as hopefully we'll do some Kubernetes CSI testing with them. And then we're looking at getting our database integrated with their Starburst instance, right? A Trino instance for a data library. And so they already have a Starburst instance that's in the cloud, and they're looking to hook it up to the vast database, and that way they can just extend what the data sets are that they're able to search through, and look for data provenance with that.
So the Trinos, because Trino is, and Starburst in general is really good at looking at multiple different data sources, and the
Yes,
vast database just becomes one more data source for Starburst to access and use. It's interesting.
exactly.
Um,
Yep. Easy to
Very cool.
integrate.
Let's talk about the future. What's coming next?
So we'll be connecting up to Kestrel. We've already tested connecting to Kestrel as a slingshot fabric, and so this is a little bit of a different configuration. We've already tested connecting to a slingshot fabric at CSCS, and we've seen great performance from it. We've seen full line rate from a individual cluster, or I mean, from an individual node, and so it's doing well. It's doing as we expect, both for throughput and for IOPS. And with that, the overhead, right? This is connecting via TCP/IP. Even with TCP/IP overhead, it was still only showing about a 13% CPU utilization on the system at its max whenever it was doing I/O. So not a terrible usage for the system. And so we'll be connecting up to their test bed, hopefully first, so that we can go ahead and kick the tires. And hopefully very soon we'll be connecting up to Kestrel in total. And being able to have that same campaign storage shared across Eagle, Kestrel, and other resources within the system. And then we have some work that we're really looking into doing with them with the data library. So using our database to ingest not only the data that we have within VAST, but also bring in logs and information from other storage systems or other resources to say what other data has been generated. And really, this is one where it will just depend on what resources we have available to play with it all, but it could be an extremely, extremely powerful way for us to, index all of the data that they're generating and really build out a data library for NREL so that they can actually see what's going on and who's doing what. And more importantly, to allow scientists to be able to say, can I find something that actually helps me to do X, Y, or Z? Am I recreating the wheel by doing this test? Has somebody already done it, right? And things of that nature. So yes, that one is really exciting, and I think something that will broadly expand the use case for for the vast system there.
Nice. So we talked a bit at the beginning about checkpointing, this very intense workload.
Yes,
We just announced some improvements on how we can help write faster and handle these really performance intensive workloads. You explain to
yes.
me how this works and then what's the change?
All right. So we have always kind of the VAST system itself has always written to a storage class memory device. And that was really just that we had a really high endurance write buffer within the system. So a write buffer is what we call it, right? It's spread across all of the SCM devices. And in our current offering, we're doing mirroring amongst them, right? Which is the fastest and easiest way to protect data, right? With the release that is going to be released later this month or early next month, we will actually be doing what we're calling write buffer erasure coding or write buffer RAID. In this case, we're going to be doing a double parity erasure code of that same data. So instead of going in and mirroring it, we're going to write across multiple SCM devices and add on some parity to it. This allows us to have a pretty significant performance improvement in the system because I'm able to write to more of the SCM devices in parallel, and I'm using less of the performance, right? If I'm looking at just pure performance, I was using 100 or 200% of the available performance for the SCM devices whenever I was fully saturated, right? With write buffer RAID, whenever I'm fully saturated, I will be using 125% or 120%, depending on how wide we can stripe it. So it gives us a pretty significant boost. I've already tested with this 5.1 release, and I have seen the 12 gigabytes per second boost that we're advertising, which is very exciting times for me, right? Because I'm building out some very large systems that are going to be doing a parallel file system workflow. And, we're getting into a system that is doing, tens of terabytes per second of write performance. And doubling write performance on a box is pretty significant whenever it comes to that, right? And so this is a pretty exciting times for us, and it addresses, the most expensive component within the system, right? Our SCM devices are the most expensive component, and now we're able to get a lot more performance out of those. So it's pretty significant.
Yeah, that makes a lot of sense. So just for other people on the call, Series is our kind of product name for the HA enclosure for the NVMe. And then, if you look here, right, so before we only made you would have 2 lines hitting 2 boxes, right? And now we've got 4 in this one. And then next we're taking it to the next level for even bigger jobs with what we're calling write buffer bursting. Tell me how this works.
So we've done a lot of analysis of all of the data that we've actually collected, and we've shown that we're being very, very nice to our SSDs within the system, right? That was the intention of what we were doing, and we kind of made a gamble very early on, said we're going to support them for 10 years, and we're still sticking with that. And actually, in what we've shown, we're actually doing quite well with that, right? We have no concerns that we're going to burn out any SSDs. And a lot of that is due to the way that we write to them. We write to them in very large chunks to the SSDs. Well, there also is this kind of a constraint in write, right? We have a set amount of storage class memory within the system, and we would like to be able to have cases where we actually want to write directly to the SSDs with our write buffer as well. Those cases would be whenever we have this very large write burst, right? And so this is kind of why I like to call it write buffer bursting. It's because on a few occasions, right, we need to actually write at higher performance than what we're able to get out of the SCM devices. Nice thing about that is that the only way that we can ever do that is if it's large writes, right? If it's large IOs. If you're doing 4K IOs, we'll never exceed what we can do within SCM, right? Because you're going to be injection limited, right? How much data you can get into the system. And so it naturally aligns that the only time that we would actually use those SSDs is whenever it's large IOs, and we can actually take those large IOs and go ahead and write them to SSDs. We'll use a little bit of the wear of those SSDs doing this, but given what we've been able to track within the system, that's completely acceptable because our wear leveling has been very nice. If we're 90% of the time we're treating the SSDs like a princess, and 10% we're throwing a little bit of extra at them, we're still going to be completely fine. And it allows us to address these, large scale checkpoint restarts, right? Which is really the pain point for, what most systems are building out all of their write performance for. Honestly, most customers will never ever see this. They will never actually utilize it, right? But whenever somebody wants us to run a benchmark, and show that we can run, at X amount of gigabytes per second, we will show that we can do it. And then once we actually get it into production, it probably will never happen again, right? But unfortunately,
hero numbers,
places, yes, it's a hero number thing. Unfortunately, a lot of places are still stuck on that mentality of I need to be able to write at this performance number because 20 years ago, it was all about checkpoint restart. And it was a single large scale job writing all of its memory down to the storage system, right? And things have changed quite a bit, right? A lot of sites aren't seeing that kind of a write performance within the system. And a lot of the sites are actually profiling their data and finding that that's true. So they're actually reducing the write performance that they need, including some of the national labs, right? There's some of them that are drastically reducing how much write performance they're writing into their requirements, right? Because they are not seeing any jobs that are actually utilizing, even on like large scale systems that have a single job running, they still are not saturating the full write performance of the system. So, so this allows us to address it and have it available if it's needed, right? But honestly, I don't know that it'll be used too much besides benchmark runs.
So the erasure coding, that's going to happen for everybody, for all workloads, even outside of HPC. And then this is for these extreme use cases. So for me, kind of the big takeaway is just I'm fascinated at how much flexibility there is within our architecture that you can make this kind of change and get this huge burst. It's not a hardware change, right? This is just software. And
Yes.
so for me, it's like, this is how software helps you get more value out of your infrastructure.
Exactly.
Awesome.
It's an amazing, amazing thing because honestly, like you can actually, I some hardware that I was running last year, put this new software on it, and I'm running at 2x, 4x the performance number, right? And so it's a pretty amazing thing that our engineering team has done for us. And I really appreciate all of their work on this
Oh yeah.
because
It's,
they've done it a very small amount of time as well, right? From
yeah.
concept to implementation, it was very quick. So they're an amazing team.
Absolutely. So much goodness coming out of there. So Kyle, thank you. I mean, every time we talk, I learn something new. It's funny. I take notes whenever you talk. And so, what I want to do is here, if you click this QR code, it's going to launch a poll. It asks you, how you want to engage us in the future. So if you've got more questions from today or, something that we showed you, you want to see a demonstration of, we're absolutely glad to set that up. You can arrange a discussion with Kyle or one of our other HPC research experts. Again, thank you for joining. Excellent session, Kyle. Thank you for your time. And we
Thank
will
you.
talk to you. We'll talk to you all in the next one. Thank you so much. Take